So after watching these videos and lectures, students are going to be able to write equilibrium expressions. You're going to be able to calculate equilibrium constants with specific values. You're going to interconvert between Kc and Kp. And of course, you're going to be able to take the shortcuts that I provide to you later on. So these are the goals and the expectations associated with this lecture series. So what is equilibrium? Equilibrium is when the rate of two opposing processes are equal to one another. So initially for many chemical reactions, we're just going to have our reactants present. And in that specific situation, the forward reaction is the only one that's possible. So A and B are going to convert to C and D initially. Now, as C and D start to build up, what's going to happen is that the reverse process is going to start to be able to occur. So C and D are going to basically produce reactants. Now, what ends up happening is that as we progress forward in this reaction to produce C and D, the rate of the reaction is going to be decreasing. Simultaneously, as we increase the quantity of C and D, the reverse process is going to increase in rate, and eventually the rates are going to become equal. Once the rate of the forward and the reverse process are equal, we're going to reach something called dynamic equilibrium. And what that means is that at that point, the concentrations of A and B and C and D are going to remain constant, and the rates of the forward and the reverse process are going to become equal. So it should be noted that the equilibrium situation means that the forward and reverse reactions are still happening. They're happening simultaneously, but the rate at which they happen are the same. So let's go ahead and look at the concept of equilibrium with respect to some graphical data. Okay, so in this first setup here, we are looking at the rate of the forward and reverse reactions, okay, with respect to time. Okay, and so what you'll notice here is that the rate of our disappearance of our reactant, as we progress through the time of the reaction, the rate of this process is going to decrease. Simultaneously, okay, as we start to produce more and more NO2, that reverse reaction starts to occur and its rate begins to increase. Now, we reach a point at which the rate of the forward and the reverse processes are the same. And at that point, we have reached equilibrium. Okay, now we can look at this same process with respect to concentration versus time. So what I want you guys to notice is initially we start out with a bunch of the reactant, and in this case none of the product. So initially no product, a bunch of reactant, and what happens over time is that the concentration of the reactant is going to decrease. Why? Because it's being converted into product. So since it's being converted into product, concentration of the product is going to be increasing. Now, what I want you guys to notice is that as the reaction progresses and we reach equilibrium, we get to the point where the concentration of products are going to be maintained throughout the reaction progression. Okay, so basically as long as equilibrium is maintained in the system, the concentration of our product NO2 is going to remain the same. The same thing is true for our reactant. Its concentration at equilibrium is going to remain the same. Okay, so that is not to be confused with saying that the concentration of NO2 and the concentration of N₂04 are the same. Okay, obviously, based on this graph, our concentration of NO2 is different than the concentration of our N₂04. Okay, so when we say that the concentration of our reactants and products remain constant, we're saying that their total concentration is the same. Okay, not that they are equal. So what are we going to see in a laboratory when we reach equilibrium? Okay, so basically there's two views. There's the macroscopic and the microscopic. The macroscopic view is what we're going to see with our naked eye. And basically, to us, we're going to look at that reaction flask or beaker or what have you, and we're going to basically observe that it seems as if the reaction has stopped or no reaction is occurring. So basically, the color change that might occur will remain the same and remain constant. Basically, we won't be able to tell that anything's happening. But on the microscopic level, the reality of it is that the forward and reverse reactions are still happening. Okay, so there's still an exchange between the atoms within the molecules and the production of more reactant and more product. Now, it's happening simultaneously, so the net concentrations of reactants and products remain the same. So let's go ahead and look at the decomposition of the N₂04 into NO2. So we've talked about the macroscopic view, that visual eyeball look at the reaction process. And we see that right here in these three pictures here. Now, what we need to know is that N₂04 is a colorless gas and that NO2 is a brown gas. Okay, so basically what we have here initially is purely N₂04. We have a colorless container that actually contains this N₂04 gas. Okay, and so basically the only thing we have present at that point is N₂04. Now, as N₂04 begins to decompose into NO2, we start to see a browning of that container. Okay, and if we look down here, notice we have N₂04 as well as the NO2 molecules that are produced from the breaking of the dimer. Okay, now as we continue to progress, we're eventually going to reach this color. Okay, and this color will basically remain constant as we maintain equilibrium in that system. Okay, and so basically we're going to have a certain concentration of our dimer, N₂04, and a certain concentration of our NO2 molecules. And basically what we have reached here is that equilibrium state. Now, to say that the equilibrium state has been reached, what that actually means is that obviously the forward and reverse reactions are still happening. Okay, the dimer is being broken down into the brown NO2 gases, and some of the NO2 gases are coming together to form the dimer, which is a colorless gas. However, the relative concentrations of these two items, the reactants and the products, are going to remain constant at that point. Okay, additionally, we know that the forward and reverse reaction rates are equal at that point. Okay, so visually, we're going to see the maintenance or the continuing darkness that we see here in this third slide, because the relative concentration of NO2 versus N₂04 will remain constant. Now, if equilibrium is disturbed, there could potentially be a shift back towards this direction, but that's something we'll discuss in more detail later. So at equilibrium, a few things are going to be true. Number one being that the concentration of reactants and products are going to remain constant. Now, this does not mean that the reactant and product concentrations are the same. Okay, so reactants concentration and products concentration, they are constant, but they do not equal each other. It's not necessarily that they're equal to each other. So please make sure, guys, that you get this into your head and differentiate that thought process. The second thing that's true is that the rate of the forward reaction is going to equal the rate of the reverse reaction. All right, so your dynamic equilibrium has been established at that point. Now, the third thing we're going to discuss is going to be that the ratio of products and reactant concentration are going to equal a constant value, and we're going to talk about that constant in detail. So the equilibrium constant is a ratio between the concentration of our reactants and products. Let's go ahead and look at the derivation of the equilibrium constant. So right here we have our forward reaction and our reverse reaction for the decomposition of the N₂04 dimer, as well as the dimerization of the NO2 gas to form the N₂04. So we've already looked at these. These are the corresponding rate laws for the forward and reverse reactions respectively. Now, at equilibrium, we know that the rate of the forward reaction and the rate of the reverse reaction are equal. So if we set these equal to one another, we end up with this relationship that we see below. Okay, and you notice the rate constant of our forward reaction divided by the rate constant of our reverse reaction is going to equal the relationship between the concentrations of our reactants and products relative to what was found in the rate laws. Okay, so this overall, guys, is going to equal our K value, or our constant, our equilibrium constant. And basically what we want to make sure we keep in our head is that the equilibrium constant represents the relationship between reactants and products and obviously their rate constants at constant temperature. Okay, and we're going to talk about K equilibrium, or the equilibrium constant, in tons of detail. So let's go ahead and let's look at writing the equilibrium expressions with respect to our products and our reactants. Okay, so remember our equilibrium constant K is equal to the relationship between products and reactants. Okay, so I have products on top, reactants on bottoms. So the equilibrium expression, in order to write it, you're going to need a balanced chemical equation. And basically, you take the concentration of your products to some power, which is going to correspond to the coefficients in front of those products, divided by the concentration of your reactants to the coefficient powers that are in front of them in the chemical equation. Okay, so basically this K value is representing Kc, which basically is telling us that that's the equilibrium situation with respect to concentration. This can be represented as Keq as well. Generally, the assumption is that we're going to be dealing with concentrations. However, we will sometimes be using partial pressures, and you'll see Kp down here. And since pressure is proportional to concentrations for gases that are specifically in closed systems, the equilibrium expressions can also be written with respect to partial pressures. Okay, so we would have the partial pressure of our product C, the partial pressure of our product D to the coefficient values, and the same thing for the partial pressures of our reactants to their coefficient values. Okay, and we'll talk about how Kp and Kc are related in a little bit. But for right now, this is just the basic form for writing equilibrium expressions. So writing equilibrium expressions are straightforward. We're going to do that for these three reactions that we see below. Now, we could be writing these with respect to Kc or Kp, depending on the type of data we're given, whether we're given concentration data for our reactants and products or partial pressure data. Depending on what we're given, obviously this is going to be represented by Kc or Kp. I'm going to write all of these as Kc expressions or with respect to concentration because usually that's how most of the problems will be handled. Okay, so if we go ahead and we look at this equilibrium expression, we have our products to the coefficient value in front of it divided by our concentration of our reactants to the coefficient value provided. Okay, so basically products over reactants to their coefficient values. So we're going to do that for these two down here. And we see these equilibrium expressions written next to each of these reactants. And basically, guys, this is how you write your equilibrium expressions. Products over reactants to the coefficient values. We will be paying attention later to the states of the reactants and products, and that will become important in the future. But for right now, we're just going to learn this basic procedure. So the equilibrium expression depends only on the stoichiometry of the specific reaction. The mechanism is unimportant because at equilibrium the forward and reverse reaction rates are equal and the ratio between products and reactants remains constant. Okay, so the equilibrium constant does not depend on how much reactant or product you start with. The only things that the equilibrium constant depend on are temperature and the specific reaction. Okay, so those are the two features that determine what your equilibrium constant is going to be. Okay, so we've been looking at this reaction over and over again. So let's go ahead and let's look at some data. So this is our equilibrium constant derived from our reactions ran in these 4 experiments. Now, what I want you to notice here is that we have different initial concentrations of our reactant. We have different initial concentrations of our products. Regardless of how we start, whether we start with no reactant and all product, or we start with all product and no reactant, or somewhere slightly in between, we end up with the same equilibrium constant within experimental error. Okay, so basically what we need to understand here, guys, is that equilibrium is going to be reached for this specific reaction. So we're going to have a specific ratio that we're going to establish at equilibrium between the reactants and products. And that equilibrium ratio is going to give us our K value. And that's going to be consistent regardless of what we start with. Okay, so remember, temperature and specific reaction is what's going to determine our equilibrium constant, not the initial amounts of reactants or products present. We're going to go ahead and write or calculate our equilibrium constants for each of the processes seen here using the concentrations above. So what we're going to do first is we're going to write the equilibrium expressions for each of these reactions using the balanced chemical equations. So now that we've written each of our equilibrium expressions with respect to the chemical equation, we're going to go ahead and plug in our concentration values and calculate our Kc values for each of these reactions. So now that we've done that for each of these, okay, we plugged in our concentrations, done the mathematical operations, and got our answers, we now have the K values for each of these chemical processes. Now we'll look at a much more straightforward approach to this process, or basically a shortcut, in a few slides. So up until now, we've primarily been writing our equilibrium expressions with respect to Kc values. Basically, the concentration of our reactants and products is the type of data that we've been provided. Okay, now we've talked about the fact that pressure is going to be proportional to concentration for gases that are in a closed system. So because of that, we can still utilize this same procedure for writing the equilibrium expressions for closed systems of gases. Okay, so basically we'll take our partial pressures of our products to the coefficient values divided by the partial pressures of our reactants to those same powers of those coefficients. Okay, so we can write our equilibrium expression in the same way we would write Kc, except obviously we write it with respect to those partial pressures. Now, I do not want you guys to think that Kc is somehow equal to Kp mathematically. Okay, so this is not true, guys. Even though we write our equilibrium expression for Kp the same way we write Kc, there are some mathematical operations that have to be carried out because we are dealing with a gas that's not dissolved in a liquid. Okay, so basically, guys, Kc and Kp are different, and we're going to look at how to actually convert between these two in the next slide. So how can we interconvert between Kc and Kp? Basically, this is the equation that you guys are going to be utilizing to make that adjustment. And basically what they've done is they've included the ideal gas law in the calculations and done some rearrangements in math. This is available in your textbook if you want to look at it. But basically this is the equation that you're going to utilize. Okay, so basically Kp is going to be equal to your Kc times your ideal gas constant, which is this one right here, so your liters ATM per mole Kelvin, times your temperature in Kelvin, okay, all to the power of delta N. And delta N, guys, is the difference between the total number of gaseous products minus the total number of gaseous reactants. Okay, and if you go ahead and plug these numbers in, you will end up with the adjusted Kp value from your Kc value. And obviously you could rearrange this and calculate your Kc from your Kp. So basically, guys, the takeaway here is you need to know this equation, how to utilize it, how to find all of the values, and that Kp and Kc are in fact different. So here they're asking us to calculate our Kc value at 25 degrees C for this reaction. Now notice they've given us Kp and they want us to solve for Kc. So we're going to have to manipulate this equation to solve for our Kc. So now that we've manipulated that equation here, we're going to go ahead and solve for Kc. Okay, so first of all, we know our constant, 0.0821 liter ATM per mole Kelvin. Okay, we know this value. Okay, we know that our temperature for 25 degrees C in Kelvin is going to be 298 Kelvin. Okay, so we also, know that constant. Okay, and our delta N, guys, is going to be our products minus reactants. Okay, so we have 2 moles of our product, NaCl, and we have 1, 2, 3 moles of gaseous reactant. Okay, so 2 minus 3 is going to give us minus 1. Now notice, guys, we're only going to count up the number of gaseous reactants and gaseous products. If we had some other phase, obviously we wouldn't include that in this calculation. So now that we have all these numbers, let's go ahead and let's plug in and calculate. So we've plugged in our values. We go ahead and plug those into our equation and then our calculator, and that's subsequently going to give us this answer below. Okay, so your gaseous reactants and products are calculated up here. You know your constant. You know how to convert into Kelvin. Basically manipulating this equation. These are all things that will allow you to calculate Kp or Kc depending on what you're provided. So by now, guys, you've probably noticed that your Kp's and your Kc values don't have any units, okay? And that might seem a little odd to you, but the reason why is because your K values are related to thermodynamic quantities and the measurement of things called activities. And activities are basically related to the ratios between components of various reactions. Okay, and what ends up happening is these ratios cause the units to cancel, and that subsequent cancellation of units leads to your equilibrium constants not having any units themselves. Okay, so I know that might seem kind of counterintuitive or odd. If you'd like to read more about it, it's in your textbook. However, if you just take it as what it is, you can move on. If you want to find out more about it, you can go ahead and read about it if you'd like. Okay, so let's continue our utilization of our equilibrium constant. So what can K actually tell us? Okay, so basically, guys, K, remember, is the ratio between products and reactants. Okay, so the bigger your K is, the larger the quantity of products that should be present relative to your reactants. Okay, and what we say when we have very large Ks is that the products dominate or predominate in that reaction, or the reaction lies to the right. Okay, if your K value is very small, we're going to say, obviously, that the reactants in that specific case are present in larger quantities. And so that reaction, the reaction equilibrium, is going to lie to the left, meaning that we have more reactants present than our products. Okay, so basically your K value can tell you the relative predominance of reactants or products with respect to a specific chemical process. So in this case, they're asking us to look at a specific reaction and the equilibrium constant values associated with that specific reaction at different temperatures. Okay, and they want us to assess if the formation of products is favored at lower or higher temperatures. So remember, guys, our equilibrium expression is going to be the concentration of our products, or the partial pressure of our products to some power over the partial pressure of our reactants. Okay, so if Kp is large, that means that I have typically more product than reactant. Conversely, the amount of reactants versus products, if I have more reactants than products, my Kp value is going to be smaller. So if we go ahead and assess our Kp values here, notice our Kp value at the higher temperature is much larger than at the lower temperature. So according to our relationship here, at the higher temperature, I'm going to have more products than reactants. So at that higher temperature, your products are going to be greater than your reactants. So the formation of products is going to be favored at the higher temperature versus the lower temperature situation. So if we continue to look at how we can work with our equilibrium expression to solve for our equilibrium constant, we can actually kind of find some shortcuts to what we've discussed previously. So previously we had our balanced equations, we wrote our equilibrium expressions, and then we plugged in our concentrations at equilibrium and subsequently did the math to get our equilibrium constant value. And so that's how we would have obtained this equilibrium constant of this specific reaction here. Now we could then plug those same numbers into the equilibrium expression for the reverse reaction and get a new answer. But what I want you to notice is that for the reverse reaction, if you take the inverse of the forward reaction, you can subsequently get the reverse reaction. So if you have information about the forward reaction or about a specific portion of the reaction, you can subsequently skip the plug-in and multiply and divide approach and utilize this in order to get your reverse reaction. So this is an easy shortcut to figuring out your equilibrium expression or equilibrium constant for reverse processes or forward processes. Okay, now if I don't give you any concentrations, obviously you're going to need to utilize these kinds of relationships, and there are more of them. We're going to look at them here in a second. Okay, so they've basically provided us with the chemical equation above here and given us the equilibrium constant for that forward process. Now, they want us to use the information that we've been given to write the equilibrium constant expression and calculate the equilibrium constant for this process. Okay, and what I want you guys to realize here is, notice we have not been provided any concentration values. Now, we've written the equilibrium expression for this process here, but notice since we don't have any of those concentration values, this approach is not going to work for us. So what we're going to have to do instead is utilize the relationship between the reverse process and our knowledge of how the forward and reverse processes are related. Okay, so we're going to use this relationship here. So in order to find the equilibrium constants for the reverse process, we're going to take and basically plug in our forward equilibrium constant into the equation here. Okay, and when we do that, we end up with 1 times 10 to the 30th. Okay, and so this is our Kc value for this process right here. Notice we didn't have any concentrations, so basically we didn't have anything to plug into here, so we needed to know this relationship in order to calculate the Kc for the reverse process. Okay, so again, let's continue to look at these shortcuts. I have this relationship here, this chemical equation. I have my equilibrium expression written here. Now, if we multiply this entire equation by 2, we end up with this this equation here. If we write the equilibrium expression for that, notice, okay, our expression looks similar, except now my exponents are different. Okay, so a shortcut approach to this, if say we didn't have our concentration values, or of course if we just wanted to kind of skip over this whole process, is that we could just utilize the relationship here. Okay, so what we do if we multiply an equation by some factor, what we do is in order to calculate the equilibrium constant for the new expression, what we do is we take the original equilibrium constant and raise it to the factor we multiplied by. Okay, so in this context, we would take our Kc value from up above and raise it to the second power. Why? Because we've multiplied this equation here through by 2 in order to derive that one. In that same way, guys, if we were to divide this equation by, say, 2, right, we are going to take that original value and raise it to the 1/2. If we divide it by 3, we'd raise it to the 1/3, etc., etc. And if we did that, obviously we'd get our K value for our new expression. In the context of adding multiple reactions, okay, if we added 2 reactions together, we can get our new expression, or excuse me, our new rate constant by multiplying the K values for each of the individual steps that we added. Okay, so these are some shortcuts that can help you guys with your calculations and basically speed up the process. Okay, so just as a nice little summary, basically we write our equilibrium expressions with respect to balanced chemical equations. Our K value is going to be equal to the concentrations of our products to some power that corresponds to the coefficients in the balanced equation, divided by the concentration of our reactants to some power that correspond to the stoichiometry or the coefficient seen in the reactants of the balanced equation. So we know how to write our equilibrium expressions. We know that we're solving for our equilibrium constant. And basically, these are the equations that allow us to easily interchange between equations. So if I know the equilibrium constant for the forward reaction, in order to find the reverse, I just take the inverse of my forward value. If I multiply a reaction through by some number, I take the original unmultiplied equilibrium constant and raise it to whatever power I multiplied by. Okay, if I've divided through, I raise that original equilibrium constant to 1 divided by whatever I divided by. Okay, and if I add 2 reactions, basically I take the K values for each of the steps that are used to produce the overall new equation, and that will give me the equilibrium constant for the new equation. So as we also discussed, the thermodynamic aspect or the activities dictate that K has no units, but we have seen that K varies with temperature. Okay, so we definitely always need to check and see that our temperatures are consistent when we're comparing specific K values.